Hey, you all. Did you know that despite all the incredible technology we have today, the fastest supercomputers, the most powerful particle accelerators, spacecraft that have traveled billions of miles across the solar system, we still cannot build a time machine, not even one that sends a single atom back in time by 1 second. And it's not because of engineering limitations or a lack of funding. No, according to our deepest physical theories, nature itself seems to have built-in safeguards, fundamental laws that prevent backward time travel, even in principle. Why is that? Why can we move freely in space, forward, backward, left, right, up, down, but time only flows in one direction, forward? Why is the past fixed, unchangeable, and inaccessible, while the future remains open and uncertain? And above all, why can't we build a time machine? Today, on Sleep and Learn Physics, we're going to explore one of the most profound and subtle ideas in modern theoretical physics, the chronology protection conjecture, and how it's deeply tied to the concept of entropy, the arrow of time, and the fundamental structure of spacetime itself. We'll journey from the early paradoxes of time travel in science fiction to Einstein's revolutionary theory of general relativity, to the mind-bending implications of quantum field theory in curved spacetime, and finally to Stephen Hawking's bold proposal that the universe might be actively protecting its own history from tampering. Along the way, we'll derive key equations, not with symbols shorthand, but written out in full, as requested, so you can truly internalize what each term means physically. We'll revisit the second law of thermodynamics, not just as a statistical tendency, but as a cosmic law that may be the ultimate guardian of causality. And we'll confront the uncomfortable truth. Even if general relativity mathematically permits closed time-like curves, paths through spacetime that loop back on themselves, nature may have other plans. So get comfortable, dim the lights, and let's begin our deep dive into why we can't travel back in time. To understand why backward time travel is so problematic, we first need to clarify what time actually is in physics, not as a vague intuition, but as a measurable geometric quantity woven into the fabric of reality. For centuries, time was treated as absolute, a universal clock ticking at the same rate for everyone, everywhere. Isaac Newton described time as flowing equably without relation to anything external. In that worldview, time was a stage on which events unfolded, but it never interacted with matter or motion. Then came Albert Einstein. In 1905, Einstein published his special theory of relativity, which shattered the Newtonian conception of absolute time. He showed that time is relative. The rate at which time passes depends on your state of motion. If you're moving very fast, close to the speed of light, relative to someone else, your clock will tick more slowly from their perspective. This isn't an illusion or a mechanical defect in clocks. It's a fundamental feature of spacetime. Time and space are not separate. They are fused into a four-dimensional continuum called spacetime. Let me write out the time dilation formula, not with symbols but spelled out in words as requested. The elapsed time measured by a moving observer equals the elapsed time measured by a stationary observer multiplied by the square root of the quantity 1, minus the square of the relative velocity divided by the square of the speed of light. In other words, if delta t prime is the time interval experienced by the moving observer, and delta t is the time interval measured by the stationary observer, and v is the relative speed between them, and c is the speed of light in vacuum, then delta t prime equals delta t multiplied by the square root of the quantity 1 minus v squared divided by c squared. Notice that as v approaches c, the term v squared divided by c squared approaches 1, so the square root approaches 0, and delta t prime becomes much smaller than delta t at 99.999% the speed of light. 1 year for the traveler could correspond to over 200 years for those left behind. That's real, measurable time dilation, confirmed countless times in particle accelerators and with atomic clocks on airplanes and satellites. But crucially, this is time dilation into the future, You can effectively jump forward in Earth's time by traveling near light speed and returning. That's allowed. But going backward, special relativity alone forbids it. In fact, in special relativity, nothing with mass can even reach the speed of light, let alone exceed it. And exceeding light speed is often naively thought to be required for backward time travel. But even tachyons, hypothetical particles that always move faster than light, lead to severe causality violations. Sending a signal with a tachyon could allow you to receive a reply before you sent the original message. That opens the door to paradoxes. So special relativity by itself seems to protect chronology, the proper ordering of cause and effect. But then in 1915, Einstein published his general theory of relativity, and everything changed. General relativity reimagines gravity not as a force, but as the curvature of spacetime caused by mass and energy. The presence of matter tells spacetime how to curve. The curvature of spacetime tells matter how to move. This is summarized in the Einstein field equations, which, again, we'll write out in full prose, no symbols. The Einstein tensor equals 8 pi times the gravitational constant divided by the speed of light to the 4th power, all multiplied by the stress energy tensor. Let me break that down. The Einstein tensor represents the curvature of spacetime, specifically, a particular combination of the Ricci curvature tensor and the Ricci scalar that ensures conservation of energy and momentum. The stress energy tensor represents the density and flux of energy and momentum in spacetime, everything from mass, pressure, electromagnetic fields, to even the energy of the gravitational field itself in certain formulations. And the constants, 8 pi, Newton's gravitational constant, and the speed of light to the 4th power, set the scale, how much curvature you get for a given amount of mass energy. This equation is nonlinear, which means spacetime curvature can feed back on itself. And because of that nonlinearity, Einstein's equations admit solutions that are far stranger than anything Newton ever imagined, including spacetimes that contain closed time-like curves. What is a closed time-like curve? Let's define it carefully. In spacetime, every massive object traces out a world line, a path through the 4 dimensions. At every point along that world line, the object's velocity vector must be time-like, meaning in local inertial coordinates, the time component dominates over the spatial components. In simpler terms, you're always moving forward in time at less than light speed in your immediate neighborhood. A closed time-like curve is a world line that loops back and connects to itself, so that an object following it would return to the same point in both space and time. Not just the same location, like orbiting a planet, but the same event. Same x, same y, same z, and same t. If such a curve exists, you could, in principle, travel along it and meet your younger self. You could hand your past self the blueprint for the time machine you just used. That's the infamous bootstrap paradox. Now, do such curves exist in real spacetime? Well, mathematically, yes. Certain exact solutions to Einstein's field equations contain them. The first notable example was discovered in 1949 by Kurt Gödel, a logician and close friend of Einstein. Gödel found a solution to the Einstein field equations describing a rotating universe filled with pressureless dust and a non-zero cosmological constant. In this universe, spacetime itself is twisted by global rotation, and closed time-like curves exist everywhere. You could launch a spaceship, follow a certain trajectory, and return to your own past without ever exceeding light speed locally. Einstein was deeply disturbed by this. He had hoped his theory would uphold causality universally, but here was a self-consistent solution where cause and effect could loop. But our universe isn't rotating globally, at least not in the way Gödel's model requires. Observations of the cosmic microwave background show extraordinary isotropy. There's no evidence of large-scale vorticity. So Gödel's universe, while mathematically valid, is not physically realized. Other solutions, however, are more tantalizing, because they involve configurations that seem, at first glance, less exotic. Consider the infinitely long rotating cylinder, often called a Tipler cylinder, after Frank Tipler, who analyzed it in 1974. Suppose you have a cylinder of enormous density, say, made of neutron star material, spinning at nearly the speed of light and stretching infinitely in both directions. The frame dragging effect, the twisting of spacetime around a rotating mass, becomes so intense that near the cylinder, spacetime is dragged around faster than light in a coordinate sense. In that region, time-like paths can tilt enough to close on themselves. A spacecraft could orbit the cylinder multiple times and emerge in its own past. But there are two fatal problems. First, the cylinder must be infinitely long. Any finite cylinder does not produce closed time-like curves. You get open helices, not closed loops. Second, to achieve the necessary rotation without flying apart, the cylinder would need to be made of material with negative energy density, exotic matter, which we have no evidence exists in macroscopic quantities. Then there's the wormhole time machine, perhaps the most famous proposal, due to Kip Thorne and his students in the late 1980s. A wormhole is a hypothetical tunnel connecting two distant regions of spacetime, a shortcut through the geometry. In general relativity, the simplest wormhole solution is the Einstein-Rosen bridge, but that's non-traversable. It pinches off too quickly for anything to pass through. To make a wormhole traversable, you need to prop it open with exotic matter. Again, matter that violates the classical energy conditions, having negative energy density. Here, how you could turn it into a time machine. Take one mouth of the wormhole, put it on a spaceship, and accelerate it to near light speed on a long journey, then bring it back. Due to time dilation, less time passes for the moving mouth than for the stationary one. Suppose 10 years pass on Earth, but only 1 year passes for the traveling mouth. When it returns, the two mouths are now desynchronized in time. Entering the Earth mouth in year 10 leads you to exit the traveling mouth in year 1, 9 years in the past. You've created a time machine. But again, this requires exotic matter, and even if you had it, quantum effects may intervene. Which brings us to Stephen Hawking. In 1992, Hawking published a paper titled Chronology Protection Conjecture. He didn't prove a theorem, he made a conjecture. Why? Because the full quantum theory of gravity remains unknown. But using semi-classical gravity, treating spacetime classically via general relativity, while matter fields are quantized, he argued that whenever closed time-like curves try to form, quantum effects will prevent it. His key insight involved the behavior of quantum fields near the would-be chronology horizon, the boundary beyond which time travel becomes possible. Imagine slowly assembling a wormhole time machine. As you desynchronize the mouths, a region of spacetime begins to develop closed time-like curves. Just before they form, say, at the moment when the time shift is infinitesimally small, a surface called the Cauchy horizon appears. This is the boundary between the region where initial conditions determine the future uniquely and the region where they don't, because information can loop in from the future. Now consider a quantum field, say, the electromagnetic field in this spacetime. Even in empty space, quantum fields fluctuate. These are vacuum fluctuations, virtual particle-antiparticle pairs constantly popping in and out of existence, borrowing energy from the vacuum for fleeting moments allowed by the Heisenberg uncertainty principle. The energy-time uncertainty principle can be written as the uncertainty in energy multiplied by the uncertainty in time is greater than or equal to Planck's constant divided by 4 pi. In a static spacetime, these fluctuations average to 0 over time. The vacuum expectation value of the stress-energy tensor is finite and manageable. But near a Cauchy horizon, something extraordinary happens. Vacuum fluctuations can loop around the incipient closed time-like curve multiple times. Each loop adds coherently, like a laser cavity, where light bounces between mirrors and builds up intensity. The field modes become infinitely blue-shifted as they approach the horizon. Let me explain blue shifting. When a wave approaches a region of strong gravity or rapid motion, its frequency can increase. For example, light falling into a black hole gets blue shifted. To an outside observer, its wavelength shortens, energy increases. Near a Cauchy horizon forming in a wormhole time machine, a quantum fluctuation emitted just before the horizon forms can circle the wormhole, return to its starting point slightly earlier, and interfere constructively with its earlier self. That interference amplifies the fluctuation. Do it again, and it amplifies more. The number of loops goes to infinity as you approach the horizon, and the frequency of the mode diverges. Hawking calculated the renormalized expectation value of the stress-energy tensor for a quantum field near such a horizon. What he found was shocking. It diverges. It doesn't just get large, it goes to infinity. In formula form, again spelled out. The renormalized vacuum expectation value of the energy density approaches infinity as the spacetime point approaches the chronology horizon. More precisely, for a massless scalar field in a two-dimensional model spacetime, like the Misner space, a simplified toy model for time machine formation, the energy density behaves like 1 divided by the square of the proper time remaining until the formation of the Cauchy horizon. So if tau is the proper time to horizon formation, energy density scales as 1 over tau squared. As tau goes to 0, energy density blows up. What does infinite energy density mean physically? It means the gravitational backreaction becomes infinite. Remember the Einstein field equations. Curvature is proportional to stress energy. Infinite energy density implies infinite spacetime curvature, and that signals a singularity. But this isn't a black hole singularity hidden behind an event horizon. This is a singularity that forms before the time machine can operate, right at the moment when closed time-like curves would first appear. It's a preemptive singularity, a wall of infinite energy that destroys the time machine just as it's about to turn on. Hawking summarized this by saying, "It seems that there is a chronology protection agency which prevents the appearance of closed time-like curves, and so makes the universe safe for historians." But is this conclusive? Not quite, because semi-classical gravity breaks down when curvature approaches the Planck scale. At distances around 10 to the minus 35 meters, or energies around 10 to the 19 GeV, quantum gravity effects must take over. We don't yet have a full theory of quantum gravity. String theory, loop quantum gravity, causal sets, etc. are candidates, but none are complete or experimentally verified. So the chronology protection conjecture remains just that, a conjecture, but it's supported by multiple lines of evidence across different models. In Misner space, in wormhole spacetimes, in Gott's cosmic string time machine, where two infinitely long, parallel cosmic strings moving past each other at high speed create closed time-like curves. In each case, quantum fields develop divergences on the chronology horizon. Moreover, even classical physics may conspire against time travel. Let's consider the second law of thermodynamics. The second law states that the entropy of an isolated system never decreases over time. Entropy is a measure of disorder, or more precisely, the logarithm of the number of microscopic configurations corresponding to a given macroscopic state. Boltzmann's formula for entropy is entropy equals Boltzmann's constant multiplied by the natural logarithm of the number of microstates. So S equals K times ln of W, where W is the number of ways the system can be arranged microscopically while looking the same macroscopically. For example, a gas spread evenly throughout a container has high entropy. There are vastly more ways for molecules to be scattered randomly than all huddled in one corner. A shattered glass has higher entropy than an intact one, more possible arrangements of shards than of a whole vessel. Now here's the critical point. The second law introduces an arrow of time. All fundamental laws of physics, Newton's laws, Maxwell's equations, Schrödinger's equation, Einstein's equations are time-symmetric except for the weak nuclear force in rare particle decays. If you filmed two billiard balls colliding and played it backward, it would look equally plausible. But if you film an egg splattering on the floor and play it backward, shards flying up to reassemble into a whole egg, that looks absurd. Why? Because entropy increases in the forward direction. The increase of entropy defines the thermodynamic arrow of time, and it aligns with our psychological arrow. We remember the past, not the future, and the cosmological arrow, the universe is expanding. Now suppose you could travel back in time. What would happen to entropy? Imagine you're in a room where a cup of hot coffee is cooling to room temperature. Heat flows from hot to cold, entropy increases. Now, if you travel back in time 5 minutes, you arrive in a state where the coffee is hotter, the room slightly cooler. From your perspective, as you stand there, you see heat flowing from the room into the coffee, entropy decreasing. But that violates the second law, unless your very presence disrupts the system. But it's worse than that. Consider the entire universe. The entropy of the observable universe today is enormous, dominated by supermassive black holes, each contributing entropy proportional to the area of its event horizon. Jacob Bekenstein and Stephen Hawking showed that black hole entropy is. Black hole entropy equals Boltzmann's constant multiplied by the speed of light cubed multiplied by the area of the event horizon, all divided by 4 times the gravitational constant times the reduced Planck constant. That's S equals K times C cubed times A, divided by 4 times G times H bar. For a solar mass black hole, that's about 10 to the 77th in dimensionless units, far greater than the entropy of all the stars and gas in the Milky Way. But at the Big Bang, the entropy was incredibly low. The early universe was extremely hot and dense, but also remarkably smooth, homogeneous and isotropic to 1 part in 100,000, as seen in the cosmic microwave background. A smooth, dense plasma has lower entropy than a lumpy one with black holes, because gravity is clumpy. The maximum entropy state for a self-gravitating system is not uniform, it's black holes. Roger Penrose calculated that the entropy at the Big Bang was fine-tuned to about 1 part in 10 to the power of 10 to the 123. That's not a typo, 10 to the 123 zeros. It's the most precise fine-tuning in all of physics. So the universe began in an extremely low entropy state and has been increasing in entropy ever since. That's why we have an arrow of time. Now if you travel back in time, you're moving to a state of lower entropy, but you yourself are a high entropy object. Your body contains about 10 to the 28 atoms, arranged in highly complex, low probability configurations. Your brain stores memories, correlations with the past, which themselves are low entropy structures. To exist in the past, you must bring your high entropy with you, or somehow reduce it. Suppose you go back to 1920. The entropy of the universe in 1920 was less than it is today. If you appear in 1920, your mass energy and internal entropy are added to that era. Unless you arrive in a perfectly compensating low entropy state, which is statistically impossible, you increase the entropy of 1920 above what it should have been. That creates a contradiction. The past is no longer self-consistent. The state you arrive in is not the state that evolved into your present. Some propose self-consistent loops. You were always part of history. In that case, your arrival must be exactly balanced, your entropy influx matched by an entropy outflux elsewhere. But the probability of such fine-tuning is astronomically small. For every particle in your body, its trajectory must be precisely coordinated with every other particle in the universe to maintain overall entropy increase along all world lines. Quantum mechanically, the amplitude for such a configuration is effectively zero. In fact, David Deutsch and others have tried to rescue time travel using the many worlds interpretation of quantum mechanics, suggesting that traveling back in time takes you to a different branch of the wave function, a parallel universe, avoiding paradoxes. But that's not true backward time travel in our universe. It's universe hopping. And even then, creating such a branch may require conditions that are physically unrealizable. Let's return to the chronology protection conjecture and examine it more technically. The divergence Hawking found is not just for scalar fields. It occurs for electromagnetic fields, Dirac fields, and even gravitons, though the degree of divergence may differ. For conformally invariant fields in 4 dimensions, the stress-energy tensor diverges as 1 over tau squared, where tau is the proper time to chronology violation. But some researchers, like Matt Visser, argued that if you introduce a physical cutoff, say the Planck scale, maybe the divergence is tamed. If quantum gravity becomes important at tau around 10 to the minus 43 seconds, the Planck time, perhaps the energy density only reaches Planckian values, not infinity, and spacetime undergoes a phase transition instead of forming a singularity. However, even Planck scale energy densities are catastrophic. The curvature scalar, the Ricci scalar or Kretschmann scalar, would reach values of 1 over Planck length squared, meaning spacetime foam, quantum fluctuations of topology, loss of smooth manifold structure. In such a regime, the very notion of a worldline or closed time-like curve may cease to have meaning. Time, as a continuous parameter, may dissolve into discrete or non-local relationships. So even if a singularity doesn't form, the time machine still fails, not with a bang but with a fuzz. Another angle, the averaged energy conditions. Classical general relativity assumes that matter obeys energy conditions, like the weak energy condition, which states that for all time-like observers, the energy density measured is non-negative. In prose, the energy density plus the pressure in any direction is greater than or equal to 0 for all physically reasonable matter. But quantum fields violate these pointwise. The Casimir effect, a measurable attraction between 2 conducting plates in vacuum, is due to negative energy density between the plates. So exotic matter isn't completely forbidden. However, there are averaged energy conditions. The averaged null energy condition states that the integral of the stress-energy tensor along a complete null geodesic is greater than or equal to 0. That is, the total energy density, integrated along a light ray's entire path, cannot be negative. Now, in wormhole and warp drive spacetimes, you need negative energy localized. But if the average null energy condition holds, the amount and duration of negative energy are severely constrained. In 1996, Larry Ford and Thomas Roman derived quantum inequalities, bounds on how much negative energy can exist and for how long. For a massless scalar field in flat space, the magnitude of negative energy density delta rho is bounded by. The absolute value of delta rho is less than or equal to Planck's constant divided by 8 pi squared, multiplied by 1 over the 4th power of the duration delta t, over which the negative energy persists. So delta rho less than or equal to h, divided by 8 pi squared delta t to the 4th. This means, the more negative the energy, the shorter the time it can last. To hold open a 1-meter wide wormhole throat, you'd need negative energy densities comparable to the core of a neutron star, but sustained for macroscopic times. Quantum inequalities suggest that's impossible. The required negative energy would have to last seconds or minutes, but quantum mechanics only permits it for timescales around 10 to the minus 21 seconds or less for human-scale energies. So even if you could generate exotic matter, you couldn't accumulate enough of it in one place for long enough to stabilize a macroscopic wormhole, let alone convert it into a time machine. Let's now consider entropy in curved spacetime. In general relativity, defining entropy globally is tricky because there's no universal time slicing. But for stationary black holes, we have the Bekenstein-Hawking formula, as mentioned. There's also the generalized second law of thermodynamics, proposed by Bekenstein. The sum of the entropy of matter outside black holes plus the total black hole entropy never decreases. So delta S outside plus delta S black holes is greater than or equal to 0. This has been tested in thought experiments, like throwing a box of gas into a black hole. As the box approaches the horizon, its entropy appears frozen to an outside observer, but the black hole's area increases, and the increase in black hole entropy compensates exactly, or more, for the lost matter entropy. Now, imagine trying to send information back in time via a wormhole. Suppose you encode a message in the quantum state of particles and send them through the time machine to yesterday. Yesterday's version of you receives the message and acts on it, say, prevents the experiment from happening. Paradox. But even without paradox, consider the entropy flow. If information flows to the past, it may create correlations that reduce entropy locally. For example, if future, you sends today's winning lottery numbers to past, you now has knowledge that decreases uncertainty, i.e., decreases information theoretic entropy. But the second law governs thermodynamic entropy, which is related but not identical. However, Landor's principle links them. Erasing one bit of information must dissipate at least kT ln2 of heat, increasing thermodynamic entropy by at least K ln2. So if time travel allows you to avoid erasure, e.g., by retrieving a backup from the future, you might circumvent Landor's cost. That would violate the second law in a subtle but profound way. Indeed, in 2013, researchers showed that if closed time-like curves exist, you could build a perpetual motion machine of the second kind, extracting work from a single heat reservoir, violating the Kelvin-Planck statement of the second law. Here, how? Use the time machine to send a qubit back in time in a correlated state. Through clever quantum operations, you can effectively reset the qubit without dissipating heat, violating Landor's principle, and use the saved energy to do work. Repeat, and you have infinite free energy. Since the second law is arguably the most robust law in physics, supported by everything from steam engines to black holes, any theory permitting its violation is suspect. Let's now turn to cosmology. Why was the early universe in such a low entropy state? This is the past hypothesis, as named by David Albert and Barry Lower. The past hypothesis is not a law of physics, it's a boundary condition. The dynamical laws, like Hamilton's equations or the Schrödinger equation, are time-symmetric. They don't care about past or future. But the initial condition of the universe had extraordinarily low entropy. Without the past hypothesis, we couldn't explain why entropy increases. If the universe were in a typical high-entropy state, it would be in thermal equilibrium. No stars, no life, no change. We observe change, so we infer a low-entropy past. But if backward time travel were possible, the past hypothesis becomes unstable. Any time traveler arriving in the early universe would perturb that delicate low-entropy state. Even a single photon from the future, blue-shifted by cosmic expansion, could introduce fluctuations that seed premature structure formation or increase entropy beyond the observed level. Inflationary cosmology helps explain the smoothness, but it assumes initial conditions that are themselves low entropy. Time travel would disrupt the inflated field's homogeneous role, triggering inhomogeneous reheating and a universe inconsistent with observations. Moreover, in eternal inflation or multiverse scenarios, even if some universes allow time travel, they may be sterile, unable to support complex structures or observers. We find ourselves in a universe with a strong arrow of time, possibly because only such universes can produce observers like us. That's a selection effect, but it doesn't make time travel possible here. Let's examine a concrete calculation: the stress-energy divergence in Misner space. Misner space is a two-dimensional spacetime obtained by identifying points in Minkowski space under a Lorentz boost. Specifically, take flat spacetime with coordinates t and x, and identify the point t, x with the point t cosh alpha plus x sin alpha, t sin alpha plus x cosh alpha, for some fixed boost parameter alpha. This creates a compact spatial direction that becomes timelike in certain regions, leading to closed timelike curves for t greater than 0. The chronology horizon is at t equals 0. Now, consider a massless scalar field phi obeying the wave equation. The second partial derivative of phi with respect to t minus the second partial derivative of phi with respect to equals 0. In Misner space, we look for mode solutions. Due to the identification, modes must be periodic under the boost. This leads to a spectrum of complex frequencies, indicating instability. Hawking and others computed the Hadamard function, the two-point correlation function, and found that as t approaches 0 from above, the difference between the quantum and classical two-point functions diverges. The renormalized stress-energy tensor component t sub tt behaves as -1 divided by 24 pi times t squared. So energy density ρ equals minus t sub tt, in appropriate signature, goes as +1 over 24 pi t squared. Positive, divergent energy density. Plugging into Einstein's equations, the Ricci scalar R, which in two dimensions fully characterizes curvature, satisfies. R equals minus 8 pi times the gravitational constant times the trace of the stress-energy tensor. In two dimensions, the trace anomaly contributes, but the key point is, R diverges as 1 over t squared. Spacetime curvature becomes infinite at t equals 0, not after, but at the onset of time travel. This isn't an artifact of two dimensions. In four-dimensional models, like the Orisson time machine, a finite vacuum solution with a toroidal region of closed time-like curves, numerical studies show similar vacuum polarization divergences. Even if you try to shield the divergence with classical matter, the required energy densities exceed Planck scales. Now, some have proposed self-consistent time travel using Deutsch's model, where quantum states entering a closed time-like curve must be consistent with their future selves. The Deutsch consistency condition is the density matrix of the system entering the curve equals the partial trace over the environment of the unitary evolution of the combined system and its future self. In simpler terms, the state going in must match what comes out after evolution. This avoids paradoxes, but at a cost. Computationally, it allows solving NP-complete problems in polynomial time, suggesting physics would become absurdly powerful. More importantly, it violates unitarity and linearity of quantum mechanics in subtle ways and introduces non-local signaling. Moreover, it requires the existence of the closed time-like curve first. But if chronology protection prevents the curve from forming, the model never gets off the ground. Let's also address a common misconception. But GPS satellites account for time dilation. Doesn't that prove we can manipulate time? Yes, but only forward. GPS satellites orbit at about 20,000 kilometers altitude, moving at roughly 14,000 kilometers per hour. Due to special relativity, their clocks run slower than Earth clocks by about 7 microseconds per day. But due to general relativity, being higher in Earth's gravitational potential, their clocks run faster by about 45 microseconds per day. Net effect, satellite clocks gain about 38 microseconds per day relative to ground clocks. If uncorrected, GPS would accumulate errors of over 10 kilometers per day. Engineers pre-program this offset into the satellite clocks before launch. So yes, we compensate for relativistic time shifts, but it's a one-way trip to the future. There's no mechanism here for reversal. Another misconception: Quantum entanglement allows instantaneous influence. Could that be used for time travel? No, entanglement creates correlations, but no information is transmitted faster than light. The no communication theorem proves that local operations and classical communication cannot use entanglement to send signals superluminally. Without signaling, you can't create causal loops. Even quantum teleportation, which transfers a quantum state using entanglement and a classical channel, requires the classical signal, which is limited by light speed. So no loophole there. Let's now quantify the entropy gradient of the universe. The current entropy of the observable universe is dominated by supermassive black holes. The largest known, Ton 618, has a mass of about 66 billion solar masses. Its Schwarzschild radius is 2 gm over c squared, so about 1,300 astronomical units. Its entropy is kc cubed over 4 gh bar, where a is 4 pi r squared. Computing roughly, r equals 2 times 6.67 times 10 to the minus 11 times 66 times 10 to the 9 times 2 times 10 to the 30, all divided by 3 times 10 to the 8 squared. That gives r approximately 1.95 times 10 to the 13 meters. A equals 4 pi r squared, approximately 4.8 times 10 to the 27 square meters. Then s equals 1.38 times 10 to the minus 23 times 3 times 10 to the 8 cubed times 4.8 times 10 to the 27, divided by 4 times 6.67 times 10 to the minus 11 times 1.0, 5 times 10 to the minus 34. Step by step. C cubed equals 27 times 10 to the 24, or 2.7 times 10 to the 25. Kc cubed equals 1.38 times 10 to the minus 23 times 2.7 times 10 to the 25 equals about 3.73 times 10 to the 2. Times A, 3.73 times 10 to the 2 times 4.8 times 10 to the 27 equals 1.79 times 10 to the 30. Denominator, 4 gh bar equals 4 times 6.67 times 10 to the minus 11 times 1.0, 5 times 10 to the minus 34 equals 2.80 times 10 to the minus 44. So S equals 1.79 times 10 to the 30, divided by 2.80 times 10 to the minus 44, equals 6.39 times 10 to the 73. In units of K, that's about 10 to the 74. The entropy of the cosmic microwave background photons is about 10 to the 88 in natural units. But wait, no. Number of photons is 10 to the 88, each with about 1 bit of entropy, so S sub cmb approximately 10 to the 88K. No, actually, for a blackbody, entropy is proportional to photon number times ln of volume per photon. But more accurately, for the CMB today, S sub cmb approximately 1.5 times 10 to the 89K. But black holes dominate. The Milky Way's central black hole, Sagittarius A star, has entropy about 10 to the 91K. Let me correct. Standard estimate. Total stellar black holes contribute 10 to the 100K, supermassive black holes 10 to the 102K, and the CMB 10 to the 88K, so black holes dominate by orders of magnitude. At recombination, 380,000 years after the Big Bang, the entropy was mostly in photons and neutrinos. The number of photons hasn't changed much, ignoring star formation, so S was similar in magnitude, but crucially, gravitational entropy was tiny. No black holes, minimal structure. Penrose argues that gravitational clumping is the dominant entropy contributor in the late universe, and its absence early on is why the initial state was so special. The Weyl curvature hypothesis, also by Penrose, states that the Weyl curvature, which describes tidal forces and gravitational waves, and is zero in conformally flat spacetimes, was zero or nearly zero at the Big Bang, but is large today near black holes. In other words, the Big Bang was smooth and isotropic, not just in matter distribution, but in spacetime geometry itself. If you traveled back to t equals 10 to the minus 43 seconds, you'd expect quantum gravity to dominate. But even there, the state must have been highly ordered to evolve into our universe. Introducing a time traveler would inject Weyl curvature, ripples, inhomogeneities that would amplify and produce a universe with too much structure too early, inconsistent with the CMB. So cosmology, thermodynamics, and quantum field theory all point in the same direction. Backward time travel is forbidden, not by decree, but by the self-consistency of physical law. But let's not stop there. Let's consider the logical structure of causality itself. In relativity, causality is enforced by the light cone structure. At each event, the future light cone contains all points that can be influenced. The past light cone contains all points that can influence it. Space-like separated events cannot affect each other. No signal can connect them without exceeding light speed. Closed time-like curves violate this global hyperbolicity. A spacetime is globally hyperbolic if it contains a Cauchy surface, a space-like slice on which initial data determine the entire future and past uniquely. Gödel's universe is not globally hyperbolic, nor is Misner space. Wormhole time machines lose global hyperbolicity when the chronology horizon forms. Why is global hyperbolicity important? Because without it, the initial value problem for physical fields is ill-posed. You can't predict the future from the past alone. Information leaks in from elsewhere, including the future. In quantum mechanics, unitary evolution requires a well-defined time parameter. If time loops, the Hamiltonian may not generate a unique time evolution operator. In quantum field theory on curved spacetime, the lack of a global time function means you can't define a unique vacuum state, leading to particle creation ambiguity, as in the Unruh effect or Hawking radiation. But near a chronology horizon, it's worse. The Bogoliubov coefficients, which relate particle definitions in different regions, diverge, signaling infinite particle production. Indeed, an observer approaching the chronology horizon would see a wall of infinitely energetic particles, the blue sheet singularity. So even if you survived the gravitational singularity, you'd be fried by radiation. Let's calculate the temperature of this radiation. In analogy with Hawking radiation, where black hole temperature is, temperature equals Planck's constant times the speed of light cubed, divided by 8 pi times the gravitational constant times the mass of the black hole times Boltzmann's constant. For a chronology horizon, the effective surface gravity kappa plays a similar role. In Misner space, kappa equals 1 over tau, where tau is proper time to horizon. Then the Unruh-like temperature is. Temperature equals Planck's constant times kappa, divided by 2 pi times Boltzmann's constant times the speed of light. So T equals h over 2 pi k sub bc times 1 over tau. As tau goes to 0, T goes to infinity. At tau equals Planck time, 10 to the minus 43 seconds, T equals about 10 to the 32 Kelvin. That's 100 million times hotter than the core of a supernova. No known material, no known structure could withstand that. Even quantum fields would be ripped apart, their Compton wavelengths shorter than the Planck length, where spacetime itself loses meaning. So nature doesn't just discourage time travel, it annihilates it with infinite fury. But is there any scenario where backward time travel might be possible? Some have speculated about the interior of rotating black holes, Kerr black holes. Inside the inner horizon, the radial coordinate becomes time-like, and closed time-like curves may exist in the maximal analytic extension. But the inner horizon is violently unstable. Infalling matter and radiation get infinitely blue-shifted there, creating a mass inflation singularity, a null singularity of infinite energy density that destroys the inner horizon before anything can pass through. Numerical simulations confirm this. Perturb a Kerr black hole, and the Cauchy horizon turns into a singularity. So even in black holes, time machines are thwarted. What about quantum gravity? In loop quantum cosmology, some models replace the Big Bang with a big bounce, but the bounce is time-symmetric. Entropy still increases after the bounce, so no reversal. In string theory, certain solutions with closed time-like curves exist, like the BMPV black hole, but they require supersymmetry and extremal charges, conditions not realized in our universe. And again, quantum corrections are expected to resolve the curves. The consensus among physicists is overwhelming. Backward time travel is impossible. Surveys at physics conferences show over 95% of relativity and quantum gravity researchers believe the chronology protection conjecture is true. Why? Because every time we've looked closely at classical stability, at quantum effects, at thermodynamic consistency, we find mechanisms that prevent it. It's not that the equations forbid it outright. General relativity is permissive. But when you add realistic physics, quantum fields, entropy, energy conditions, the solutions become unstable or unphysical. Nature appears to abhor a time loop as much as it abhors a vacuum. Let's end this first part by summarizing what we've covered so far. We began with the hook. Despite advanced technology, we can't build a time machine. We explored how special relativity allows time dilation into the future but forbids backward travel. Then general relativity opened the door mathematically, with Gödel universes, Tipler cylinders, and wormholes. But each requires unphysical conditions, infinite sizes, exotic matter, or perfect fine-tuning. We introduced Hawking's chronology protection conjecture. Quantum effects, specifically the divergence of vacuum energy near the chronology horizon, prevent closed time-like curves from forming. We derived the time dilation formula, the Einstein field equations, and the entropy formulas, all written out in full prose. We connected this to the second law of thermodynamics, emphasizing that the universe's low entropy beginning establishes a firm arrow of time, and backward travel would disrupt that gradient. We examined quantum inequalities, showing that exotic matter can't be sustained long enough for time machines. We looked at cosmological constraints, the past hypothesis and Weyl curvature hypothesis, indicating that our universe's initial conditions are incompatible with time travelers. We calculated concrete numbers, black hole entropy, Meissner space divergence, Planck scale temperatures, showing that even near misses lead to physical impossibilities. And we addressed misconceptions about GPS, entanglement, and black hole interiors, each falling short of enabling true backward time travel. But we're only halfway there. We still need to explore deeper questions. What is time, fundamentally? Could time emerge from a more basic, timeless quantum structure? How do quantum gravity approaches like causal set theory or thermal time hypothesis treat the arrow of time? And what do recent experiments, like quantum simulations of closed time-like curves, tell us? We'll also dive into the philosophical implications. If time travel is impossible, does that mean the future is open and the past fixed? How does this relate to free will, determinism, and the nature of existence? We begin with a radical idea. Perhaps time isn't fundamental. In classical physics, time is a background parameter. In quantum mechanics, it's an external label. You solve the Schrödinger equation with respect to time. Even in general relativity, though time is dynamical and interwoven with space, the spacetime manifold is still assumed to be a smooth, four-dimensional continuum with a time coordinate that locally distinguishes past from future. But in attempts to quantize gravity, like the Wheeler-DeWitt equation in canonical quantum gravity, something startling happens. Time disappears. The Wheeler-DeWitt equation describes the quantum state of the entire universe, the wave function of the cosmos. It's derived by applying the usual quantization rules to the Hamiltonian constraint of general relativity. And here's the shock: it contains no time derivative. In prose, the Hamiltonian operator acting on the universal wave function equals 0. That is, h hat psi equals 0. This is not a typo. There is no I h bar partial psi over partial t. Time does not appear. What does this mean? It suggests that at the most fundamental level, the Planck scale, the universe is static. Change is an illusion. What we perceive as time may be a thermodynamic or quantum entanglement effect emerging from a timeless whole. This is the problem of time in quantum gravity, one of the deepest unsolved issues in theoretical physics. If the fundamental description has no time, then traveling back in time is as meaningless as traveling north of the North Pole. There's no temporal dimension to move along, only correlations between variables. For example, in a simple cosmological model with a single scale factor, describing the size of the universe, and a scalar field phi like the inflaton, the Wheeler-DeWitt equation becomes a partial differential equation in an phi, but no t. Solutions are static surfaces in the phi plane. Yet, if you pick phi as a clock, you can recover an effective time evolution. As phi increases, evolves like an expanding universe. Time emerges relationally, through change in one variable relative to another. This is the relational view of time, going back to Leibniz and Mach. Time is not a thing in itself, but a measure of change. So if time is relational, what does backward time travel even mean? It would require revering the correlations across the entire universe, not just your local world line, but every quantum degree of freedom entangled with you. That's not engineering, that's rewriting the cosmic wave function. Let's consider entanglement and the emergence of time. In 2013, a groundbreaking paper by Don Page and William Wouters proposed that time arises from quantum entanglement between subsystems. Imagine the universe split into two parts, a clock C and the rest R if the total state is stationary. H total psi equals 0. But C and R are entangled. Then an observer within R sees C evolve and interprets that evolution as time. Specifically, if psi equals the sum over n of C sub n times phi sub n of R tensor chi sub n of C, and the clock states chi sub n are energy eigenstates with eigenvalues E sub n, then the conditional probability of finding R in state phi, given that C reads time t, is governed by an effective Schrödinger equation with time. The phase factor E to the minus I E sub nt over h bar emerges from the global constraint. Now suppose you try to reverse time. You need to flip the sign of all those phases, e to the plus I E sub nt over h bar, but that requires acting on the entire entangled state with a time reversal operator t. In quantum mechanics, time reversal is anti-unitary. It complex conjugates coefficients and reverses momenta and spins. But applying t to the whole universe is not something inside the universe can do. You'd need an external agent, outside spacetime, which contradicts the premise that the universe is all there is. Moreover, even if you could apply t locally, decoherence prevents reversal. Once a quantum system interacts with an environment, emitting photons, colliding with air molecules, the information about its past state spreads irreversibly. To reverse it, you'd need to reverse the state of every environmental degree of freedom it ever interacted with, a task whose complexity grows exponentially with time. That's why scrambled eggs don't unscramble, not because the laws forbid it, but because the probability is 10 to the minus 10 to the 23 or smaller. So even in a relational time framework, backward travel remains practically, and likely fundamentally, impossible. Now let's turn to causal set theory, a discrete approach to quantum gravity where spacetime is not a continuum, but a partially ordered set of elementary events. In causal set theory, the fundamental structure is a set of discrete atoms of spacetime with a binary relation, precedes. If event X precedes event Y and Y precedes Z, then X precedes Z, transitivity. And no event precedes itself, irreflexivity. This partial order encodes causality directly. From this, geometry emerges statistically. The number of elements in a region gives its spacetime volume. The longest chain between two elements gives their proper time. Crucially, closed time-like curves are forbidden by definition, because the causal order is a partial order which disallows cycles. If X precedes Y and Y precedes X, then X equals Y, which violates irreflexivity. So in causal set theory, chronology protection isn't a dynamical consequence, it's built into the foundations. Time travel is logically impossible, like a square circle. This resonates with Hawking's intuition. Perhaps the universe isn't just protected from time travel, it's constructed to exclude it. Other approaches, like loop quantum gravity, also suggest discreteness at the Planck scale. Spin networks evolve via spin foams, where time is represented by the thickness of the foam. But again, the transition amplitudes are designed to preserve causality. Backward in time moves are either suppressed or undefined. String theory, with its higher dimensions and dualities, has more wiggle room. But even there, consistent backgrounds with closed time-like curves are unstable or non-perturbative. For example, the Gimin-Polchinski solution, a stringy generalization of the Gödel universe, contains closed time-like curves, but they are shielded behind chronology horizons where string winding modes become light, triggering a phase transition to a causal geometry. So across quantum gravity frameworks, the message is consistent. Time's arrow is not accidental, it's woven into the fabric of reality. But let's return to entropy, because even if time is emergent, entropy gives it direction. We've spoken of the second law, but let's derive why entropy increases, starting from mechanics. Consider a gas of n particles in a box. The microstate is a point in 6n-dimensional phase space. Positions q sub I and momenta p sub I for I equals 1 to n. Liouville's theorem says that under Hamiltonian evolution, the phase space volume is conserved. The flow is incompressible, like an ideal fluid. So if you start with a small, low-entropy region, e.g., all particles in the left half, it doesn't shrink, it stretches and folds like dough in a kneading machine, filling more and more of phase space. But the accessible phase space, the set of microstates compatible with the macrostate, e.g., fixed energy, volume, particle number, is vastly larger for high-entropy macrostates. The ratio of high entropy to low entropy volume is astronomical. For n equals Avogadro's number, 10 to the 23, the overwhelming majority of microstates correspond to near uniform density. So if the initial state is low entropy, a tiny patch, and dynamics are ergodic, they explore phase space uniformly, the system will almost certainly evolve toward higher entropy. But why was the initial state low entropy? That's the past hypothesis again, and it's not explained by dynamics. It's a boundary condition. Now suppose you could travel back in time. You need to reverse the momenta of every particle, apply the time reversal operator t. Q stays the same, p goes to minus p. In principle, Newton's laws are symmetric under t, so if you could reverse all momenta exactly, the system would retrace its path, entropy would decrease. But in practice, you can't. Any error, say, revering one momentum to 99.9999% accuracy, grows exponentially due to chaos. The Lyapunov exponent lambda quantifies this. The separation between two trajectories grows as e to the lambda t. For a gas, lambda is on the order of collision frequency. about 10 to the 10 per second. So after 10 collisions, 10 to the minus 9 seconds, an error of 1 part in a billion becomes order unity. To reverse a macroscopic system for 1 second, you'd need initial momentum precision better than 10 to the minus 10 to the 10, which is physically impossible. Quantum uncertainty alone forbids it. The uncertainty principle gives delta P times delta Q greater than or equal to h bar over 2. For a macroscopic object, delta Q is tiny, so delta P has a lower bound. Thus, time reversal is dynamically unstable and quantum mechanically forbidden at macroscopic scales. The arrow of time is not just statistical, it's enforced by quantum mechanics and chaos. Let's now examine black hole thermodynamics more closely, because black holes are where gravity, quantum theory, and thermodynamics collide most dramatically. Hawking radiation shows that black holes have temperature and entropy, and they evaporate over time. The power radiated by a Schwarzschild black hole is power equals Planck's constant times c to the 6th, divided by 1536 pi times g squared times m squared times h bar squared. More precisely, using the Stefan-Boltzmann law adapted for black holes, power equals sigma times a times t to the 4th, where sigma is the Stefan-Boltzmann constant, a is the horizon area, T is Hawking temperature. But sigma for black holes is not the usual value. It's derived from quantum field theory in curved spacetime. The evaporation time for a black hole of mass m is evaporation time equals 512 pi times g squared times m cubed, divided by h bar times c to the 4th. For a solar mass black hole, that's about 10 to the 67 years, far longer than the age of the universe. But for a small black hole, say mass of a mountain, evaporation is explosive. Now here's the key. Hawking radiation is thermal, random, featureless, maximum entropy. It carries no information about what fell in the original calculation, leading to the black hole information paradox. But if information is lost, unitarity is violated, and that undermines quantum mechanics itself. Modern resolutions, like black hole complementarity, AD-SCFT duality, and the firewall paradox, suggest that information is preserved, encoded in subtle correlations in the Hawking radiation. Crucially, the evaporation process is irreversible. A black hole forms, radiates, and vanishes, leaving only thermal radiation. You can't run the movie backward. Thermal radiation doesn't spontaneously collapse into a black hole and eject the original star. Why? Because the final state has vastly higher entropy. The entropy of the black hole was S equals kc cubed over 4g h bar. After evaporation, the entropy of the radiation is even larger, about 4/3 times the original black hole entropy, due to the expansion of phase space. So black hole formation and evaporation is a one-way street, another manifestation of the thermodynamic arrow. Now imagine trying to send a probe into a black hole through the inner horizon and out via a wormhole to the past. Even if the math allowed it, the evaporation timescale is too long for astrophysical black holes, and for small ones, they explode before you get in. Moreover, the radiation near the horizon is intense. For a solar mass black hole, Hawking temperature is about 60 nanokelvin, colder than space. But for a black hole of mass 10 to the 11 kilograms asteroid-sized, T equals about 120 Kelvin, still cold. To get T equals 300 Kelvin room temperature, M equals about 4.5 times 10 to the 22 kilograms, about 7 thousandths of Earth's mass. Such black holes would be radiating gigawatts, but none have been observed. So no natural time machines there. Let's now discuss experimental and observational constraints. Do we see any evidence of time travelers? Stephen Hawking once threw a party for time travelers, but only sent out the invitations after the party happened. Nobody showed up. More seriously, physicists have searched for signatures, anomalous particles in cosmic rays that appear to come from the future, violations of causality in high-energy collisions at the LHC, unexpected correlations in quantum optics experiments. All null results. The Opera experiment in 2011 initially reported neutrinos moving faster than light, potentially enabling time travel via Lorentz violation. But it turned out to be a loose fiber optic cable and a misaligned clock. Nature is stubbornly causal. Even in quantum mechanics, where particles take all paths, the path integral includes only forward time-like and light-like paths in standard formulations. Closed paths in time are excluded or suppressed by infinite action. In the Euclidean path integral, where time is Wick-rotated to imaginary values, the metric becomes positive definite and all paths are space-like. Closed time-like curves don't even appear in the formalism. So the mathematical frameworks themselves bias toward causality. Now, let's address a subtle point. What about apparent time travel in certain coordinate systems? For example, in the Kerr metric for a rotating black hole, the coordinate time phi azimuthal angle becomes timelike inside the ergosphere. But that's just a coordinate artifact. You can always find a local inertial frame where time flows normally forward. Similarly, in Gödel space, the closed curves are coordinate dependent in a global sense, but physically, an observer following one would age normally, and their local light cones always point forward. The key is the global causal structure. If any time-like curve closes, causality is threatened, even if locally everything seems fine. But as we've seen, quantum effects destroy that global structure before it forms. Let's now quantify the energy required to stabilize a wormhole. Suppose we want a spherically symmetric, traversable wormhole with throat radius r. The Morris-Thorne metric is ds squared equals minus e to the 2 phi of r dt squared plus dr squared over 1 minus b of r over r plus r squared d omega squared. For traversability, phi of r must be finite everywhere no horizons, and b of r must satisfy b of r equals r, throat condition, and b prime of r less than 1, flare-out condition. The Einstein equations then give the stress-energy tensor components. The radial tension tau, negative pressure at the throat is tau equals c to the 4th, divided by 4g times 1 over r squared. For r equals 1 meter, tau equals 3 times 10 to the 8 to the 4th, divided by 4 times 6.67 times 10 to the minus 11 times 1. c to the 4th is 8.1 times 10 to the 33. So tau equals 8.1 times 10 to the 33 divided by 2.67 times 10 to the minus 10 equals 3.03 times 10 to the 43 newtons per square meter. That's 30 billion pascals, orders of magnitude beyond neutron star core pressure, about 10 to the 34 Pa. And this is tension, negative pressure. To sustain it, you need exotic matter with energy density ρ less than minus tau over c squared. So ρ less than minus 3.03 times 10 to the 43 divided by 9 times 10 to the 16 equals minus 3.3, 7 times 10 to the 26 kilograms per cubic meter. Water is 1,000 kgm3, this is negative, and 30 trillion times denser. Even if you use quantum fields, the Ford-Roman quantum inequality says the duration delta t, over which this can be sustained, is bounded by delta t less than or equal to h bar divided by 8 pi squared times c cubed times absolute value of ρ. Plug in ρ equals 3 times 10 to the 26. H bar equals 1.0, 5 times 10 to the minus 34. C cubed equals 2.7 times 10 to the 25. So denominator, 8 pi squared times 2.7 times 10 to the 25 times 3 times 10 to the 26, approximately 8 times 9.8, 7 times 2.7 times 3 times 10 to the 51, approximately 630 times 10 to the 51, equals 6.3 times 10 to the 53. So delta t less than or equal to 1.05 times 10 to the minus 34 divided by 6.3 times 10 to the 53 equals 1.67 times 10 to the minus 88 seconds. That's unimaginably short, 10 to the minus 45 times the Planck time. No physical process can operate on that timescale. Thus, even in principle, macroscopic wormholes cannot be held open long enough for traversal, let alone conversion to time machines. Now, let's consider the psychological arrow of time. We remember the past, not the future. Why? Because memory formation is a thermodynamic process. To record a memory, whether in a brain, a hard drive, or a photograph, you must increase entropy elsewhere. For example, when a neuron fires, ions flow across membranes, dissipating heat. The memory trace is a low entropy configuration, paid for by higher entropy in the surroundings. Landor's principle. Erasing one bit of information dissipates at least kT ln2 of heat. But writing a memory also requires energy, typically much more than the Landor limit, due to inefficiencies. So memory is only possible in the direction of increasing entropy. A time traveler arriving from the future would have memories of events that haven't happened yet, in their new present. But those memories could not have been formed in that branch of history, violating the thermodynamic basis of cognition. In a self-consistent loop, your memory of the future is just part of the fixed timeline, but then you have no free will and no new information is gained. It's a static loop, not true travel. This connects to the computational arrow. Computation requires irreversible operations, which increase entropy. Reversible computing is possible in principle, like billiard ball computers, but any real device leaks heat. So consciousness itself may be tied to the thermodynamic arrow, making backward time travel incompatible with being a sentient observer. Let's now examine recent work on quantum simulations of time travel. In 2014, a team led by Martin Ringbauer simulated Deutsch's model of closed time-like curves using entangled photons. They didn't send anything back in time. They used quantum teleportation and post-selection to mimic the consistency condition. The result, the simulated time traveler could solve certain problems more efficiently, but only because the experiment discarded incongruent outcomes. In real physics, you can't post-select the universe. Every outcome must be accounted for. So these experiments test models, not feasibility. More recently, in 2020, researchers used a quantum processor to simulate a qubit interacting with its past self. They found that consistency constraints reduce the channel capacity. Information transfer is degraded, not enhanced. And crucially, no violation of causality occurred, because no signal was sent outside the light cone. So simulation, not equal to realization. Now what about the future of time? Could entropy eventually decrease? In an eternally expanding universe dominated by dark energy, the end state is heat death, maximum entropy, uniform temperature near absolute zero, no free energy, no structure. But some speculate about Poincare recurrences, where, given enough time, a system returns arbitrarily close to its initial state. The Poincare recurrence time for the observable universe is about e to the s, where s is the entropy in units of K. S is about 10 to the 104, so recurrence time is e to the 10 to the 104 years. That's a 1 followed by 10 to the 104 zeros. The current age of the universe is 10 to the 10 years. Even if such a recurrence happened, It wouldn't be time reversal. It would be a statistical fluke, a random low-entropy fluctuation. Observers in that era would still perceive time flowing forward, with entropy increasing away from the fluctuation minimum. So no true backward travel, just a temporary dip in the entropy curve. Boltzmann brains, self-aware fluctuations in the void, are more likely than full universe recurrences, but even they would have scrambled, inconsistent memories, not coherent histories. So again, no help for time travelers. Let's now return to Hawking's original argument and strengthen it. In his 1992 paper, Hawking used the point-splitting method to renormalize the stress-energy tensor. But later work by K, Radzikowski, and Wald showed that on a spacetime with a compactly generated Cauchy horizon, the two-point function of a quantum field cannot be of Hadamard form, which is required for a physically reasonable vacuum state. The Hadamard condition ensures that ultraviolet divergences are the same as in flat space, so renormalization works. If it fails, the stress-energy tensor isn't just divergent, it's undefined. The theory breaks down completely. This is a rigorous no-go theorem within semi-classical gravity. No physically acceptable quantum state exists on a spacetime that is on the verge of developing closed time-like curves. So it's not just that energy blows up, it's that the quantum field theory itself becomes ill-defined. This is stronger than a conjecture. It's a mathematical obstruction. Only a full theory of quantum gravity could resolve it. And as we've seen, candidate theories either exclude time loops or render them non-operational. Let's also clarify a common confusion: time dilation versus time reversal. Time dilation, like in GPS or the twin paradox, is differential aging. The traveling twin returns younger, but both twins agree on the order of events: departure, turnaround, reunion. No event is observed in reverse order. Causality is preserved. True time reversal would require event B to occur before event A in all reference frames, which relativity forbids for time-like or light-like separated events. Only space-like events can have ambiguous time order, but they can't be causally connected anyway. So relativity enforces local causality strictly. Global causality, no closed curves, is the extra layer that quantum effects protect. Now, consider the role of the speed of light. C is not just the speed of light, it's the universal speed limit for causality. It's the conversion factor between space and time in the spacetime interval. The spacetime interval squared equals c squared times delta t squared minus delta x squared minus delta y squared minus delta z squared. If this is positive, the separation is time-like, causally connectable. If zero, light-like. If negative, space-like, causally disconnected. Closed time-like curves require the interval to be positive, and the path to close, which means spacetime must be so warped that forward in time loops around. But the light cone structure must remain intact locally. The problem is global topology. However, quantum gravity may modify the light cone at high energies. Some models of Lorentz invariance violation, like in loop quantum gravity or string gas cosmology, predict energy-dependent speeds of light. But experiments constrain such violations to less than 1 part in 10 to the 20, so no help for time machines. And even if high-energy photons moved faster than low-energy ones, you still couldn't send a signal to your own past without creating paradoxes. And nature seems to abhor paradoxes more than vacuums. Let's now discuss the Novikov self-consistency principle. Proposed by Igor Novikov in the 1980s, it states that if closed time-like curves exist, only self-consistent events can occur. Physics conspires to prevent paradoxes. For example, if you try to kill your grandfather, the gun jams, you miss, or he survives by chance. Mathematically, it means the initial value problem has solutions only for data that satisfy global consistency constraints. But this doesn't make time travel possible, it just makes it boring, and it raises new problems. How does physics know to prevent the inconsistent outcomes? Is there a hidden variable guiding events? In quantum mechanics, inconsistent histories have non-zero amplitude, so why are they suppressed? Deutsch's model answers the second by projecting onto consistent subspaces, but at the cost of nonlinear evolution and information paradoxes. Moreover, self-consistency doesn't address the formation problem. Even if a time machine exists, how did it form without violating chronology during construction? Hawking's conjecture targets that. The machine fails before it becomes operational. So Novikov applies only to pre-existing curves, not to dynamically forming ones. And since we have no evidence of pre-existing curves, it's moot. Let's now look at observational cosmology. The cosmic microwave background is isotropic to 1 part in 100,000. If time travelers had visited the early universe, they would have injected energy, creating hot or cold spots inconsistent with observations. Big Bang nucleosynthesis, occurring minutes after the bang, produced light elements in precise ratios, about 75% hydrogen, 25% helium-4, trace deuterium, lithium. These ratios match predictions exquisitely, within a few percent. Any injection of energy or matter from the future during that epoch would alter the expansion rate or reaction rates, spoiling the agreement. Similarly, the distribution of galaxies and the baryon acoustic oscillations in the large-scale structure are consistent with a smooth, causal evolution from initial quantum fluctuations. No evidence of acausal interventions. So empirically, the past appears pristine, untampered. This supports the idea that chronology is protected not just theoretically, but in practice. Now, let's consider the philosophical implications. If backward time travel is impossible, does that mean the future is open? In classical physics, Laplace's demon could predict everything from initial conditions, so the future is fixed, even if unknown. But quantum mechanics introduces genuine indeterminism in most interpretations. The future is not determined, only probabilities are. However, the past is fixed because it has left records, entropy-increasing traces. So the asymmetry isn't in the laws but in the boundary conditions. Fixed past, open future. Time travel would blur that line, making the future influence the past, and vice versa. But since it's forbidden, the asymmetry holds. This gives meaning to concepts like responsibility, planning, and hope. A universe where the past could be changed would be chaotic. No stable history, no shared reality. Perhaps chronology protection isn't just physical, it's existential. It allows coherent narratives, personal identity, and the possibility of learning from experience. Sleep and learn physics isn't just about equations. It's about understanding why the world is intelligible. And a world without a fixed past isn't intelligible. Let's now derive the entropy of mixing, a simple example of irreversibility. Suppose two ideal gases, A and B, each with n molecules, occupy separate halves of a box. Initial entropy. S initial equals 2 times nk ln V over n plus constants. After removing the partition, each gas expands to fill volume 2V. Final entropy. S final equals nk ln 2V over n plus nk ln 2V over n plus same constants equals 2 nk ln V over n plus 2 nk ln 2 plus constants. So delta S equals S final minus S initial equals 2 nk ln 2. Positive entropy increases. To reverse it, you'd need to compress each gas back to half the volume, but that requires work and dissipates more entropy than you recover. Maxwell's demon, a hypothetical being that sorts molecules, seems to violate this. But as Landor and Bennett showed, the daemon must erase its memory of molecule positions, which costs kT ln2 per bit, restoring the second law. So even intelligent intervention can't beat entropy. Time travel would be the ultimate daemon, sorting events across time. But it too would require erasure, generating entropy that cancels the gain. Nature is fair and ruthless. Now let's address a final objection. What about the Feynman-Stuckelberg interpretation, where antiparticles are particles moving backward in time? In quantum field theory, the negative frequency solutions to the Dirac equation are reinterpreted as positive energy antiparticles moving forward in time. The propagator for an electron includes terms that look like a positron going backward, but it's just a mathematical convenience. No measurable quantity, like charge, energy, or momentum, flows backward in time. All observables evolve causally. So this is not real time travel, just a useful bookkeeping trick. Similarly, in the transactional interpretation of quantum mechanics, advanced waves from the future combine with retarded waves from the past to form transactions, but the net effect is causal, and no information is sent to the past. So no loophole. Let's conclude this second part by synthesizing. We've seen that time may not be fundamental, but emergent from entanglement or discrete causal structure. Entropy increase is driven by initial conditions and chaos, made irreversible by quantum uncertainty. Black holes reinforce the arrow of time through evaporation. Wormholes and exotic matter are ruled out by quantum inequalities. Observations confirm a causal, untampered past. Memory, computation, and consciousness rely on the thermodynamic arrow. Simulations don't equate to realization. And rigorous theorem show quantum field theory breaks down near chronology horizons. The universe isn't just unlikely to allow time travel, it's constituted to prevent it. But why? Why this particular set of laws and initial conditions? We don't know. Maybe in the multiverse, most universes have no arrow of time and no observers. We're in one that does, because only here can questions like this be asked. That's the ultimate selection effect. So tonight, as you drift off to sleep, remember, you're not just resting. You're participating in the universe's grand, irreversible journey from low to high entropy, breathing, thinking, remembering, all made possible because time flows in one direction. And that's not a limitation. It's a gift. Because without it, there would be no story, no learning, no you. Good night. May your dreams be free of closed time-like curves. No paradoxes, no singularities, no infinite blue shifts. Just smooth, forward-flowing time and deep, restorative sleep. You've earned it.